Hey guys, welcome back to my channel. Today we're going to talk about the routing protocol BGP. There are many routing protocols used on the internet like OSPF, BGP, ISIS, RIP, IGP, EIGRP, etc. Now all these protocols are basically protocols which are run on the physical networks, but now we do have the software defined networks as well. And these networks also use its own routing protocols. Okay, so we are mainly going to discuss about the BGP and OSPF since I think these are the most widely used, and having an understanding of these two protocols will help you understand how the other protocols would also work. So today I'm going to give you a brief introduction about BGP in this video. Okay, the BGP is also called as Border Gateway Protocol. It is basically used to communicate information between its neighbors through a process called BGP peering. BGP routers establish peering sessions with each other to exchange routing information and maintain a consistent routing tables. So how does the routing protocol work? It basically has to form a BGP peering with all its neighbors, whichever it is connected to, and it will exchange information about whatever network it knows about to the other one. Okay, then this is done via BGP peering. The aim is to use the routing table to reach a particular destination IP address via the best possible path. Okay, internet has many routes to the same destination. As I've told you before, it has a lot of fault tolerant network in its backbone. There are a lot of TCMP parts, a lot of load balancing parts, so it has to determine which particular route is better, and this routing protocol basically helps in choosing the best path. We have millions of routers on the networks running on the network, right? So BGP uses the notion of autonomous system. Okay, remember this autonomous system AS, where an entire organization or a routing domain that consists of multiple networks and routers are assigned a single autonomous system, and the route exchange happens between the devices and different and in the same autonomous system, as we'll see later in the video. Okay, the AS number is a 4 byte number. Earlier it used to be 2 bytes, 1265535, but now they have increased to 4 bytes, which is about 16 million. So this is not like available easily. It has to be purchased. It has to be purchased by an international standard called IANA. Okay, you have to follow certain rules and regulations and comply with certain principles and this thing. Only then you will be issued an IANA, an AS number. Okay, so generally large organizations that have their own data centers and multiple routers and networks, they purchase this. The ISPs purchase this. Okay, so in your, let's say I have a Facebook data center will purchase an AS number and will use that AS number to form a peering with another AS. Say ISP has AS 200, and all the routes will be exchanged of between these two ASs via the BGP peering. Okay, which we'll see in an example later. Okay, now let's say you are part of a local area network, uh, but you are not a big organization to be able to afford an autonomous system, right? So what happens in that case? Let's say you're living in an apartment which has about 200 houses, or you're living in a society. Okay, and your internet provider is Airtel or Verizon or AT&T, and they have an edge router which converts your private IP address into public IP address using the NAT protocol. And this NAT protocol, after it's converted into a public IP, is able to communicate with the outside world, right? So your ISP would put that particular edge router into an autonomous system assigned by the ISP. Make sense? So you don't have to put money; it's already assigned to you by the ISPs. Okay. So this is how the exchanging of information happens between different autonomous systems, and since it's like a huge network, there will be millions and billions of routers and routes. Using AS numbers helps in maintainability. It's easy to maintain when you just have to learn each other's routes via like the AS number assigned. Okay, now BGP is a path vector protocol. So what do you mean by path vector? Path vector means, as a routing protocol, its main duty is to exchange route prefixes along with its main principle is to just exchange route prefixes, but BGP also exchanges route attributes. Okay, route attributes are nothing but certain characteristics of the route, okay, that will be associated with the prefix. Now let's say these characteristics are configured by you as a network engineer. You will configure these route attributes. This route attributes could be a preference, it could be the weight, it could be the AS path, the number of hops it has taken to reach a particular destination. So each AS zone it goes through, each AS system it goes through, autonomous system it goes through, it will prepend its AS number onto it and it will send it out. Okay, so the shorter the sequence, the better path it is. Consider like that. There is like the router ID, there is an origin protocol, the route has been originated from which protocol, is it an OSPF, is it a IGP route, is it a static route. Okay, so all there is a hierarchy. We'll go through that hierarchy. If there is a tie, then we go to the next one. If there's a tie, we go to the next one. So like that, the path, whichever one breaks the tie, will be chosen as the best path. Okay, makes sense. We'll see that, like how that happens. Okay, in the software as well, when you write right, you first compare, let's say the first one is the weight, and then its preference, and then it's the AS path sequence length. So if all of them are tied, then we go to the fourth one could be maybe origin or the lower router ID. So there are different hierarchy in the route attributes. I think we can just read about it a little bit about it offline and see which one comes first. Okay, so that helps us making the decision to choose the best path. Okay, now previously as I mentioned that there are two types. There's BGP peering, and there are two types of BGP peering. One is external BGP and one is internal BGP. Okay, by forming this BGP peering, you're able to get the route updates. Okay, so any routing protocol will generally form peering with each other, and then they'll exchange the route information. BGP does the same, and this one is using external BGP. In external BGP is basically two devices which are part of two different autonomous systems form a peering. Okay, let's say I am Facebook. My AS path is AS number is 100, and I have an ISP which I want to communicate with, whose AS path is 200. So I have to form an eBGP because the AS numbers are different over here. Okay, what BGP does is it basically forms a TCP connection first. Once the TCP connection is formed, the route updates are exchanged, which consist of IP prefixes and associated attributes of those prefixes. Okay, so eBGP is basically very crucial for sharing routing information between different parts of the internet. Okay, like eBGP will help you know about the different routes that you can reach which are on the internet. Okay, by sharing all the information from other ASs as well to your AS. So your AS knows how to reach any other AS in the entire world. Okay, then the next one is IBGP. Okay, now IBGP is an internal border gateway protocol, which is basically a peering formed between two routers within the same autonomous system. Okay, I can have IBGP peering formed within the same autonomous system also. Okay, as long as those two are reachable. Okay, so over here also we use the same TCP peering is used to form the connection. Once the connection is formed, the routers will exchange the routing information, and which will help in maintaining a consistent routing table within the AS. Okay, IBGP ensures that routers within the same AS have the same view of the external routing information. That means, like, let's say device 1 and device 2 will have the same routing entries in their table to reach the outside world. Okay, my like device 1 can also reach a particular IP, and device 2 can also reach the same particular IP if it's in the outside world. Okay, and it's not necessary that it has both the devices have to be able to reach each other, or they have to be able to reach any other device on the same IBGP network. Okay, but it should be able to reach the same eBGP prefix if it wants to. So IBGP ensures that all of them within the same IBGP have the same external routing information. Okay, now these are the two types of peerings. which we are going to talk about in detail in the coming video. Now, how is this peering formed, right? So now this peering is formed by sending some messages. Okay, there are four types of messages: open message, update message, keep alive message, and notification message. Okay, along with these messages, there are also certain states. There are certain BGP states. Okay, and there is like a control chart which I'll share with you guys. Please go through it. But let me just give you a brief detail on about those different states. So whenever there are two devices which are configured with BGP, okay, what happens is it goes into idle state. Okay, the first state is idle state. Idle state is where BGP waits for a TCP connection from a peer. Okay, then once the TCP connection, the three-way handshake is formed, it moves to connect state. Okay, once the TCP handshake is formed, it moves to open send state. Open send state is when TCP connection is formed and the device waits for an open message from the peer. Now this open message will basically consist of the BGP version. It will consist of the router ID. It will consist of the AS number, the source address. It will consist of any authentication like MD5 used, or some different flags. Okay, this will also help in determining whether it is a eBGP connection based on the AS number or IBGP. Okay, so when we are in the open send state, we are waiting for the open message to be received from the peer. Okay, once the peer and the device agree on this open message, they see the version is matching, the router ID is fine, authentication is fine, everything is fine, it's eBGP. Then what will happen is the device will send a keep alive message. Okay, it will start sending keep alive messages. Once the keep alive message is received, it will, by the device, it will move to open confirmed state. Okay, so open confirmed state is like, okay, both the devices have agreed to this peering, and then it will move to open confirmed, and then it will move to established state. Okay, established state is when you start sending the update messages, you start sending the notification messages and keep alive messages. So what are these update messages? Okay, so update messages basically are the route exchange messages. This includes the information about the IP prefixes, associated attributes such as AS path, next hop, etc. Okay, or any policies or constraints which are applied. Now, what are keep alive? BGP routers periodically exchange keep alive messages to maintain the BGP session. These are like hello messages. Okay, so if default value is 60, and there'll be a whole timer of into 3, which will be 180, which is 3 minutes. So if you don't receive this keep alive messages for 3 minutes, that means there is an issue with the BGP connection, and it can trigger a re-establishment of a session. Okay, so again it will go to the idle state. Okay, now what happens once it moves to idle state, right? It will form a TCP connection again. What if the TCP connection is not formed? If the TCP connection is not formed, then it goes from connect to active state. Active state is where there is something called as connect retry timer. Okay, let's say by default it's configured as 60. So after 60 seconds, it will move to idle state and again try to form a TCP connection with the peer. Now again the TCP connection is not formed. What will happen? Again it will go to active state. It will again retry the timer. The timer is connect retry timer is reset. Now this time it will be reset to double the value it was set before. So it first was 60 seconds. Now it will wait for 120 seconds, and then it will go to idle state and again wait for a TCP connection. Okay, now this process keeps repeating. Okay, until the TCP connection is formed and it moves to open send state. Okay, then there is something called as notification messages. Notification messages is, let's say the BGP peering is reset, or the TCP connection has gone down, the whole timer has expired, and it needs to disconnect the session, right? So an error code is sent via this notification messages to the peers. Okay, now these are the different types of BGP messages, and these are the different types of states that it can move to. Okay, so I'll share a link with detailed description. Please just go through it once, and about the different messages and the different states. Okay, so now also remember that BGP communication is based on principle of incremental updates. Okay, instead of sending the entire routing table each time, BGP routes are only exchanged based on the updates. If there is a route withdrawal, then it will only send the route withdrawal information. If there is a route addition, then it will only send the new route. Okay, so there's not too much of information being sent at once. Okay, and this makes the protocol more scalable. Remember that, because there are millions and millions of routers and routes which you have to learn, which you have to have in your routing table in order to reach the internet. So it's very necessary that you don't you, you have to make this protocol scalable as well. Okay. um, Also, as I mentioned before, that once you go from one AS to another AS and then another AS to another AS, right, at each AS it will prepend its AS number and it will send it out to the other AS. Okay, let's say from AS 100 it started the packet, the you have to learn the address from AS 100, so it will first send 100, then it goes to 200 AS, it will be prepended with 200, so it's 200 comma 100, then it will be prepended with the next one, which is say 300 comma 200 comma 100. And let's say there is a loop which goes back to 100. Okay, so first what it does is it will first check the AS sequence and see if its AS number is present in that AS sequence. Now if it's gone back to AS 100, then 100 will still see that okay, my AS number is already present in the sequence, that means there is a loop, so I'll discard this packet. So this AS path sequence is also used for determining loops. Okay, like in L2 we have STP. Over here the BGP protocol uses its own AS sequence to determine if there is a loop in the network. Okay, so yeah, so over here IBGP routers have the information about all the routes sent by the EBGP, and EBGP basically has all the information about all the routes which are there on the internet. Okay, which it is learning from different autonomous systems. So routes learned by the IBGP routers are not sent to other IBGP routers. Remember that. Only EBGP routes learned by IBGP routes are forwarded to other IBGP routers. So a router can be configured both, if it's a gateway router, it can be configured both as EBGP, which is facing the other AS, and the interface that is facing the other AS, facing its own AS, will be IBGP. Okay, so that's how that particular router will learn about all the uh, paths in the it will be able to share that information about its own routes, which are originated from its own AS, and give it to the EBGP, and EBGP will be able to give it to its peer, which is part of different AS, that these are the routes in my AS. Okay, similarly, if it has learnt route from a different AS, that also will be given to it, that these are the routes from my AS and these are the routes from this other AS, and that information will be there in the AS part with the AS sequence. Okay, since it will have the AS number of the other this thing as well. Okay, I hope, yeah, I hope this makes sense. So one other thing is, whenever we have IBGP configured in an autonomous system, there is a necessity that we form a full mesh topology within the single AS that has IBGP running. Okay, the full mesh topology is necessary if we want to share the information about different autonomous systems to different EBGP peers. Okay, I'll show you this with an example why full mesh is required, and since, and it's not necessary that this full mesh has to be basically a physical connection between all the devices. Okay, it, as long as these interfaces are reachable by, let's say, running another routing protocol underneath, like say OSPF or RIP or something, you should be fine. It does not have to be a physical connection. And in order to avoid this entirely, we also have some concept called as route reflectors. Okay, so we'll talk about that also in another video. Okay, and route reflectors and route confederations, which is basically to avoid this full mesh topology. We'll discuss more on that. So this process allows BGP routers to build and maintain a consistent view of the network's topology, enabling them to make informed decisions about the best paths for routing data between different networks. So this is how EBGP has all the information about the routes present in a different AS, and the IBGP routers have the information about all the routes present on the internet, which it will learn from its EBGP routers. Okay, I hope you guys understood about IBGP, EBGP, you have understood about, different route attributes. You have understood about the different BGP messages and what are the different BGP states. Uh, I will share a link with you. You can go in detail about all of this. This was just an overview I wanted to give you on BGP. So tomorrow we'll go over an example to see how the route prepending, how the AS path prepending happens, how EBGP is formed, how IBGP is formed, how full mesh topology is formed. Okay, which will give you more insight on it. Uh, until then, please do let me know, guys, if you have any questions. Please like, share, and subscribe. Thank you.